This is trigonometry, section 5.5, where we're going to be working with some new formulas. In fact, quite a bit of new formulas. We'll probably do one or two examples from each of the sections of new formulas. But remember, I'm giving you these formulas on a test, and so it's just really important that you know how to apply these formulas and use them within the context of the question. And so we're going to be using multiple angle, power reducing, half angle, product to sum, and sum to product formulas. But again, I remind you, I'm giving you these formulas on a test. So often these equations, these formulas are used in trigonometry and then eventually in calculus. Believe me, I've asked our AP calculus teacher if there's any of these that I can kind of cut out, and he has said absolutely not. So we are definitely going to make sure we at least introduce these formulas to you. So for those of you that go on to calculus, you have seen some of these before. So our first one are called double angle formulas, and you'll notice we have the sine of 2x or 2 mu, right? And here is the breakout. Now cosine of 2 mu has a couple of different, we have 3 different options that we can choose from. And to know which option to choose is one of those things, the more you practice it, the more you figure out which one to use. It's almost like you've got to look ahead and try to determine which one it is you want to use. And then we have the tangent of 2 mu as well. All right, so let's get into our first example. We have 2 cosine x plus sine 2x equals 0, and we need to solve for x. And so we're going to have general solutions where we're going to have to add that 2 pi n at the end so that we cover all of our bases when it comes to all of the correct solutions to this. And since I see the sine of 2x in there, I'm going to use my double angle formula that says the sine of 2x is equal to 2 sine x cosine x. So that's the first thing I'm going to do, is I'm going to keep 2 cosine x, but I'm going to change this to 2 sine x cosine x. Now I'm going to take out my GCF between these two, which is 2 cosine x, so I wind up with 1 plus sine x. I then set each of my factors equal to 0. So I get the sine of x is equal to -1, and the cosine of x is equal to 0. So even though we've had both cosine and sine, since we didn't have any squareds, I was still able to solve it just by factoring. So the sine of x is, that occurs at 3 pi over 2, and I need to add 2n pi, so that's one of those solutions. And then the cosine of x, well, that occurs at pi over 2 and 3 pi over 2. So we've got x equals pi over 2 plus 2n pi. Now notice I didn't write down the 3 pi over 2 because it's already covered by this solution. So we can kind of generalize these two together. If you wrote this on your homework, it would be 100% correct. But another way to write this is just pi over 2 plus n pi. And that covers all of these solutions for both this cosine and this sine solution. Right, let's move on to example 2. I like this one because we're going to go back to drawing a triangle. Use the conditions below to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. And you'll notice I included our little cheat sheet here so that we can use it as we go through. But the first thing I'm going to do is I'm going to draw a triangle in the coordinate plane. And I want to make sure I draw it in the proper location. Right here, this tells me that I'm in quadrant 4. Right, so let's draw a triangle in quadrant 4. Does not have to be drawn to scale. Here is going to be my theta value. Now the cosine of this angle here is 5, so adjacent over hypotenuse, and I've got to do the whole Pythagorean theorem to figure out what this side is. I know just by looking at it, it's a Pythagorean triple, so I know this side is going to be a 12, but because we're in quadrant 4, I'm going to make it a -12. So I've kind of drawn my triangle, which is perfect. I now need to figure out these 3 things. So in order to figure out the sine of 2 theta, I'm going to use this equation here that says 2 sine theta cosine theta. So what is the sine of theta, right? Opposite over hypotenuse. So negative 12/13. What's the cosine? Well, they already told us in the setup, 5/13. I'm going to plug this all into my calculator and simplify it as a fraction. I get negative 120 over 169. Now let's figure out cosine of 2 theta, and I know I have a couple of different ones I can use, so really you can kind of pick any one you want. I'm going to pick 2 cosine squared theta minus 1, just because since they gave us cosine to start off the example, why not use that? I know that that's a correct answer. So if like on a test, you know that cosine theta is 5/13, so why not use that? So I get 2 times 5/13 squared minus 1 equals, when I put that into my calculator, I get negative 119 over 169. And then our last one is tangent of 2 theta. I have to calculate what my tangent value is, but then I'm going to plug it into this equation here. So the tangent of theta, we got opposite over adjacent, so negative 12/5 divided by 1 minus negative 12/5 squared. Plugging all of that into my calculator, making sure I'm taking my time as I do it, you should get out 120 over 119. All right, that's why I like that one, right? We've got some good triangles in there. Okay, this one, I'm going to try to make sure, I'm almost going to write it out as a proof so that we can really see what we're doing here. So I've got the sine of 3x. I don't see a 3x over here. I only see a 2x. So I'm going to rewrite this. The sine of 3x is equal to the sine, notice where my parenthesis is at, is right here, right? I've got to make sure I calculate this here. And actually, once we go through some additional examples, we're gonna kind of see how we're able to do this. Now, do you remember our sum formulas from our last section that we just finished? Well, if you don't have those, I should have copied that over here so we could see it. You can use the sum formula that we have for the sine of 2 angles added together here. Let me break that out for you. It's sine of 2x cosine of x plus cosine of 2x sine of x. And I'm going to write that we're using our sum formula from 5.4 to get that breakout. So now once I've done that, I do see that I have, right, some of these double angles in there where I'm going to have to use a double angle formula to replace those parts. So I'm going to highlight those in red just to make sure we kind of keep track of what's what. So the sine of 2x, that's 2 sine x cosine x, and then I still have this other cosine x, plus, now the cosine of 2x, right, again it's difficult to know which one to use. I'm going to use 1 minus 2 sine squared x, and then I still have that other sine x. Hopefully all will be revealed while we're doing this. Here is our double angle formula. Now I'm going to kind of combine what I have here, right? I have 2 sine cosine squared x. I'm going to have to distribute this sine through, plus the sine of x minus 2 sine cubed x. Really, right there we just kind of distributed to get that. Now let's see, what should we do here? Oh, cosine squared. Maybe there's a way to replace cosine squared with a sine. Then I could have everything in terms of sine. Well, remember our Pythagorean identity that says this. I can replace, if I subtract sine squared x from both sides, I can then change this to 1 minus sine squared x. So I have 2 sine x times that plus that. All right, I'll write down here I distributed. Here I'll write Pythagorean identity. All right, now let's go ahead and distribute this through. I get 2 sine x minus 2 sine cubed x. I've got plus sine x minus 2 sine cubed x. Okay, so hopefully now we can just kind of combine our like terms. These two can be added together, and these two can be added together. So when I simplify down, it doesn't really matter in which order you write them, I get 3 sine x minus 4 sine cubed x. I know that's kind of an ugly answer, but really what we did is we kind of used all of these different formulas and identities and whatnot to rewrite this, because it says, right, to rewrite it all in terms of sine x. So that's why I wanted to use those double angle formulas. That's why I didn't want to use the one here that included cosine and sine. I wanted to use the one that was just sine. Here, that's why I wanted to remove the cosine squared x and rewrite it as 1 minus sine squared x. So there we go. Okay, our next group of angle formulas is called the power reducing formulas. And you'll notice these are for sine squared, cosine squared, and tangent squared. So let's go ahead and look at an example. We want to rewrite sine to the fourth of x in terms of the first powers of cosines of multiple angles. So that means I'm not allowed to have any squareds, and I have to only have cosines in my answer. And I've kind of put the power reducing formulas down here so we can see. And you'll notice up here, it already shows me my answer. So if I put sine to the fourth of x or sine to the x raised to the fourth power into Desmos, this is the curve that I will see. This is the answer that we're trying to get to. So I'm giving you the answer ahead of time. This is what we're trying to get to. So let's start working on this. I know sine to the fourth of x is basically sine squared x squared, right? So that way I get to work with just a sine squared x, and I know I've got an equation here for that. And that, right, is going to be equal to 1 minus cosine of 2x over 2 raised to the second power. So I'm going to have to raise this whole numerator to the second power and my denominator to the second power, which means in my numerator, unfortunately, I must FOIL. Oh, 1 minus 2x, 1 minus cosine. Okay, so once I FOIL that out, I get, and you'll notice they're starting to put the number out front, so maybe I'll rewrite this with the 1/4. I'll bring this kind of out front as a fraction, so I can just kind of work on one level here. I get 1 minus 2 cosine 2x plus cosine squared of 2x, because there's a 2x there, so I've got the cosine of 2x squared. All right, so I've got cosine squared. So I still wound up with a squared. I wanted a first power, but I got a squared out of it. It's a good thing that I have this equation down here that I can now plug in for this. But when I plug it in, my mu, the value here is 2x. So I'm going to wind up with 2 times 2x when I plug it in here. So I've got 1/4. 1 minus 2 cosine 2x, that's kind of fine where it is, plus 1 plus cosine of 4x over 2. Now I'm a little bit stuck. What do I do? What do I do? Well, this is 1/2, and this is cosine of 4x divided by 2. I'm going to break that out into 2 separate fractions here. So I'm going to go ahead and erase that so that I have a little bit more room to work with. So I'm going to rewrite that as 1/2 plus the cosine of 4x over 2. They mean the exact same thing. I've just broken them out so that I know I need to combine some like terms here. But let's distribute this through. Let's really take care of this 1/4 because it's kind of getting in the way. I got 1/4 minus 1/2 cosine of 2x plus 1/8 plus the cosine of 4x over 8. Okay, now what I'd like to do, I want to get it to look exactly like this, right? First, I need to combine these two together. So it's 1/4 plus 1/8. That's 3/8. So I know that's there. So I've got a 3/8 minus 1/2 cosine 2x plus 1/8 cosine 4x. I am going to distribute, I'm going to basically, factor out a 1/8. That means I then have to have a 3 up front. I have to have a minus 4 cosine 2x, so that if I were to distribute this back through, I get a 1/2 plus the cosine of 4x. And these mean the same thing, okay, right? We got the answer here. Now, if you got it down to kind of this answer and you didn't kind of take out this fraction, this very last step, I would be completely acceptable with it. You have done your duty of making sure you're in the first power of multiple angles. But since I had this picture up here that we gotten from your book, I wanted to make sure I showed you how you got to that specific answer. All right, so that's our example working with those power reducing formulas. Here, our next one, we did double angle formulas. Here are the half angle formulas. And notice it's basically, if I want to calculate the sine of half of an angle, I do have an equation that I can use here. But just be warned, you have to know in which quadrant that half angle is, because that will tell you whether or not it's positive or negative. And that's a little bit confusing, right? But we'll be able to think about that. So first we want to find the exact value of sine of 105 degrees. So exact value means no decimals. I have to have square roots in my answer. Now, 105 degrees, that's in quadrant 2, and in quadrant 2, sine is positive. So when I use this half angle formula, I'm not going to have to worry about positive or negative. I know it's going to be positive. Now, the reason why I'm using a half angle equation is because 105 degrees is half of 210 degrees, which is on our unit circle. So that's why if we have to do exact values, we want to be able to use our unit circle. So let's use 210 degrees. So I'm going to calculate the sine of 210 degrees divided by 2, which is 105, so it looks just like our equation here, equals the positive square root of 1 minus cosine of 210 degrees divided by 2. So let's pull out our unit circle. Let's go ahead and look at what the cosine of 210 degrees. It's the square root of 3 over 2 divided by 2. We got a lot of stuff going on here. All right, so now we need to figure out the best way to simplify this. Wait, cosine of 210, that should be a negative, right? So then this should make it a positive. So I get the square root of 1 plus square root of 3 over 2 divided by the square root of 2. I've got to simplify this down, and when I do, it simplifies down to the square root of 2 plus the square root of 3. Notice that's kind of involved in there, divided by 2, because I have to get rid of that square root of 2 in my denominator. All right, moving on to our next example. We've got to find all solutions of this in our interval specified, so I don't have to worry about all of the different multiples. And I can tell just by looking at this equation here, I'm going to use my half angle formula for cosine in here. So I am going to replace, so when I plug this in, I'm going to have 1 plus cosine squared x, that's perfectly fine, equals 2. Now, since I don't know what angle it is, I don't know where it's located in what quadrant, I am going to plug in the entire thing, the positive and the negative. And remember, this thing, based on the equation up here, is being squared. And that's going to be a nice thing, because when we square a square root, what happens to it? It completely goes away. So I wind up with this nice equation, which really is not too bad to work with. My 2's are going to nicely cancel out there. So I wind up with 1 plus cosine squared x equals 1 plus cosine x. Now we know how to solve these. I'm going to subtract everything, move it over to one side, so I get cosine squared x minus cosine x equals 0. My 1's have canceled out. I then factor out my GCF. I set each of my factors equal to 0. And now I just have to figure out between 0 and 2 pi, what are my solutions? Well, cosine of x is equal to 1 at x equals 0. Cosine of x is equal to 0 at x equals pi over 2 and 3 pi over 2. Final answer there. All right, moving on, we're now up to the product to sum formulas and the sum to product formulas. So product to sum formulas are used in calculus quite a lot. These are definitely ones that we want to cover. They're solved involving the products of sines and cosines of two different angles. So you can't just kind of add, if I'm multiplying the sine of mu times the sine of v, I can't just multiply those two things together. I have to use an equation for them. So in our first example, they're saying, okay, you've got the cosine of 5x times the sine of 4x. So I've gone ahead and copied that product to sum formula that we're going to need to use, and my angle value, so my u is 5x and my v is 4x when I plug it into this equation here. So we're going to get 1/2 times the sine of 5x plus 4x minus the sine of 5x minus 4x. So that's going to equal down to 1/2 times the sine of 9x minus the sine of x. And then if we need to distribute this 1/2 through, just kind of depending on the question, depending on if it's a multiple choice question or whatnot, here is our final answer. So this one really not too bad as long as you have those formulas in front of you and you know you're using the correct one. Not too bad. Now sometimes we may have to reverse the whole process and say, all right, what if I have the addition of 2 and now I want to convert it into a product, right? I want to go from sum to product. Then these are the formulas that I'm going to need to use. So in example 8, I know I'm going to be adding the cosine of 195 degrees plus the cosine of 105 degrees, and they want it to be exact. So I'm going to go ahead and hope that when I go through this process, I get angles that end up being on my unit circle. So my u value is 195 degrees, my v value is 195 and then 105 degrees, and I'm going to plug them into this equation. So I get 2 cosine of 195 plus 105 divided by 2 times the cosine of 195 minus 105 divided by 2. And when I do that, lo and behold, very nicely, I do get some angles that are on my unit circle. So I get 150 degrees and 45 degrees, and I know I can calculate the cosines of that. So I get 2 times negative square root of 3 over 2 times square root of 2 over 2. And when I simplify that down, I get negative square root of 6 over 2. And since I don't have a radical in my denominator, I'm good to go. Just keep it simplified like that. Example 9 is going to be very similar. But now they want us to solve. Notice how this is now set up as an equation. It is equal to 0. So I have to figure out what values of these angles are going to work in here. So we've got our u value is going to be 5x. Our v value is going to be 3x. And I'm going to plug it into this equation. 5x plus 3x divided by 2 cosine 5x minus 3x divided by 2, and it equals 0. So I get 2 sine 4x cosine x equals 0. So what this really means is that this whole thing is already factored down. I am multiplying these three things. And in order for these three things to be multiplied together, either the sine of 4x has to equal 0 or the cosine of x has to equal 0. Well, the cosine of x equals 0 at pi over 2 and 3 pi over 2, right? Let's say we're solving this on the interval 0 to 2 pi, just to make it a little bit easier. Now, we want to know what angles, right, have a sine of 0. Well, the angles that have a sine of 0, right, that's going to be at 0, pi, 2 pi, right, if I keep going around, that kind of thing. So it's 0 plus pi n. So we're going to say 4x is equal to 0 plus n times pi. But I want to divide by 4. So when I do that, right, I'm going to wind up with all of these different fourth angles that are going to work. X can equal pi over 4. It can equal pi over 2, but we already knew that. It can equal 3 pi over 4. It can equal 4 pi over 4, which is just pi. It can equal 5 pi over 4. It can equal 6 pi over 4, but we already knew that, 3 pi over 2. It also can equal 7 pi over 4. So I know 1, 2, 3, 4, 5, 6, 7, 8 answers that we have there, or 7 answers that we can use. Oh, I forgot 0. I was going to say we should end up with an even number of answers. So, but we also have to consider 0. I should have put that first because that's our smallest one. And if you want to prove this, right, show this graphically, you can put this into Desmos. Type in the sine of 5x plus the sine of 3x and just find all of the different x-intercepts. You will see all of these are x-intercepts for that equation in Desmos. All right, let's get to our last example, our real-world example. Ignoring air resistance, the range of a projectile fired at an angle theta with the horizon and with an initial velocity of v sub 0 feet per second is given by this equation, where r is the horizontal distance that the projectile travels, right? So the projectile is going to kind of come out, right? It's going to be kicked, and we're going to have this type of angle that's created, and r is the horizontal distance that projectile eventually travels. So we've been looking at these types of equations. We've been modeling them with just kind of quadratic formulas, or at least we did quite a lot of that in Algebra 2 and pre-calculus and stuff. Now what we're going to do is we're going to use an equation that uses velocity and the sine of the angle and the cosine of the angle. So the velocity is, a football player can kick a football from ground level with an initial velocity of 80 feet per second. No idea if that is fast enough. Write the projectile motion model in a simpler form using only the first power of a sine of a multiple angle. So that's why I included this double angle formula up here. I want to try to take this equation and rewrite it as just the sine of 2x, or 2, in this case, theta, because that's what we have here. But right now, I just see sine theta, cosine theta. I need to have a 2 out front here. Well, the way that I can have a 2 out front here is I can take 1 over 16 and make it 1 over 32. That way, right? I haven't changed the value. 2 over 32 is still 1/16, but now this looks exactly like I wanted it to look. So I get 1 over 32 initial velocity squared times the sine of 2 theta. So that is the equation that we are going to use to then solve letter B, which is at what angle must the player kick the football so that it travels 200 feet. So I'm going to go on to my next slide, so I have some space here. So I have 200 is equal to 1 over 32. My initial velocity was 80 times the sine of 2 theta. And I have to square that 80 because that's what our equation says. Plug this into my calculator. I get this. Divide both sides by 200. I get 1 equals the sine of 2 theta. So I have to consider what angle, and let's talk about it in terms of degrees, has a sine of 1. So the angle that has a sine of 1 is 90 degrees. So therefore, the player needs to kick the ball at an angle of 45 degrees so that it will travel 200 feet. So that sums up section 5.5 and our unit. So at the end, this is the end of our unit. You have homework questions assigned for 5.5. Thank you.